In this lesson, we'll go over figure refinement and 3D plotting, which will be a good follow-up to our previous lesson in 2D plotting. We have 5 learning objectives this time. It's to improve the visualization of a plot using grid lines and spatial scaling. The second is to apply TeX markup script to improve the appearance of string outputs. The third, to create dynamic character strings by linking numeric arrays to strings with the number to string command. The fourth, to create additional plots within the same figure using Subplot, which is an amazingly powerful function. And the fifth is to insert professional looking figures from MATLAB into Word documents. So what we're going to do mainly here is we're going to use this time to get some more practice with the plotting commands, to get more comfortable with what you learned last time, and then we're going to apply some more advanced refinements to these figures as you prepare them for professional communication, whether it's with homework or for your job. And so just as a side note, don't screenshot MATLAB figures for documents that you're going to submit. I mean, screenshots are great for emails, they're great for message boards, but they're just really not good for documents. There's some good export commands, and we'll talk about later about using a copy and paste command for Word documents in particular. So pull open the starter code, which is called Triangle Coordinates in 3D Starter Code.m. And what we're going to be doing is we're going to be creating a plot that looks like this. So it's a triangle on the left with 3 vertices. You can see that it's in 2 dimensions. And then on the right hand side, we have a 3-dimensional plot that uses those same coordinates but adds a z-axis to give it that spatial depth. In the starter code, there's already 3 sections of pseudocode in which first are defined vertices of the triangle using Cartesian coordinates, and you'll notice that these are the same 3 points in the x and y that we used before when we used the geometry of a triangle function. And so then below that, we'll first plot the 2D figure, which you saw on the left just a moment ago using the x and y coordinates, and then the next part in the pseudocode, add a 3D plot as a panel to the right side of the 2D plot. So let's start down here making the 2-dimensional plot, and so we'll use our normal plot command, and we need to put an array of x coordinates, y coordinates in there. And so x1, x2, and x3 is our array, then comma, y1, y2, and y3. And so let's save this and let's run and see what we come up with. And you'll notice here that when we plot this, we don't have a triangle yet. And so we need to close the triangle. If we've got our first coordinate, second coordinate, third coordinate, we need to close it among this side. And so we'll do that by adding, going back to the first coordinate, x1, x2, x3, and then we need to add an x1 to close the triangle, and then we need to add a y1 to close the triangle in y. When we run this again, we see that we get the triangle that has the closed line. So, all right, so let's add some line specs to this, and let's just do something simple. So let's make it blue. We'll make it a regular line with circles being our markers, and then let's add a line width. Run it, and we should have blue with circles. That's a 3-point line. And now that we have our triangle in 2 dimensions, let's start refining this plot. One more step that I always like to add in my figures is a command called grid on. And you'll see that when we run this, it creates a background of construction lines that allows us to be able to see really clearly that this is 0, 4, this is 0, 2, and then this is 4, 1. But one thing to notice here that's a little bit annoying is that if we were to draw this same triangle on a sheet of grid paper by hand, it wouldn't look like what we have here, because the y-axis grid has units of 1 meter per grid, and then the x-axis has units of 0.5 meter per grid line. And so this is a 2-to-1 aspect ratio, and it results with our triangle being distorted. And so when you have data that you're plotting, that can be, like I said, kind of annoying, but it doesn't give you, in this case, because it's spatial information, it doesn't give you an accurate representation of the triangle. And so there are properties in MATLAB that you can adjust these aspect ratios for the axes. And so in these axis properties, to make this a 1-to-1, we're going to add a command that says axis equal. And so there are several of these axis properties that you can check out, but certainly when you have data that are the same units on the x-axis and the y-axis, this is a good way to get a better representation. Now, I don't recommend this at all if you have time on the horizontal axis and then some values or variables that you're plotting on the y-axis, or some other mixed variables, because the scaling that MATLAB chooses is often quite good, and I think you'll find that to be true. All right, so now remember, our goal here is to make this figure publication ready to hand in to a professor, ready to send to a colleague, ready to publish in a paper. And to be honest with you, I don't quite like this yet. And the reason why is because how often is it helpful to have a plot in which all the data points are right on the edges of the plot? So we can, quote unquote, zoom out by adjusting the limits and making them wider than what we need for the triangle, and then taller than what we need in the vertical direction. So let's adjust our limits so that we have 1 meter of margin around each of these vertices. So let's do that by our xlim command, which we already know. And so in the xlim command, we're going to make it from -1 to +4. And for the y limits, we're going to set that with an array from -4 to 4. And so that's going to allow us to get that 1 meter margin that we need on each side. Let's run that and see how that looks. And I see I messed up. It looks like that needs to be a 5 to be able to get the margin that I want on the vertical axis, and a 5 on each of those. There we go. So let's correct that. And now, there we go. So we have a properly scaled axes in which we have margin around our plot so that we can accurately see the triangle, and that we've got a little bit of breathing room around our plot. And so you can see that compared to where we started, which was a distorted triangle with thin lines, and then not quite the breathing room that you needed, there's a drastic difference with some simple commands like grid on, axis equal, xlim and ylim, that you can drastically change the look of your figure and make that look a lot more refined and professional. And really, this is just the beginning. If you can imagine any type of figure, there's likely a way to get exactly what you want in MATLAB with some of the more advanced commands. All right, next, let's start refining text annotations. So we'll put text annotations in, similar to what we did in the last class. The first one that you always need are X labels and Y labels. So let's work just with the X label. And in the X label, remember, we're going to put a string inside of the parenthesis, and we'll be able to plot out whatever string we have. So on our x-axis, we've got x1, x2, and x3. So we run it, we should be able to get that string in a normal font at the bottom of our plot. And then, we often use subscripts for our data. So the x1 coordinate would be x sub 1, x sub 2, and x sub 3. And so let's start talking a little bit about some markup commands that we can use. And one of those is to put an underscore in between the main word and then the word or number that you want to be a subscript. And so when we run this with our x underscore 1, x underscore 2, and x underscore 3, then you see that that's exactly what we get. We get an x sub 1. And so let's make that more generic. Let's just say this is just going to be our x chords. So for x coordinate system that we're going to have on this axis. And so an x underscore chords, short for coordinates. And if we run that, then we get an interesting result. We see that we have an x, and then the C is the subscript, but then the rest of the word, OORDS, are in the normal font and in the normal size. And so what we're doing here is we need to figure out our way around this, and the way to do that is to put curly braces. So x underscore open curly brace, chords, and close the curly brace. And so what we've got here is we're starting to introduce some new syntax that has been around for a long time. It's a particular type of markup script called TEX, and that's spelled T-E-X, and was the precursor to LaTeX, if you've used that. This has been around since, I believe, the late 70s. And it's a very, very powerful tool for controlling typesetting. And it's especially useful for typesetting really complex mathematical formulas that you need to come out just the right way. And so, but just it happens to be in the syntax that tech uses curly braces instead of parentheses. So when you use this, it really makes any of these commands, honestly, it makes anything in your text look really, really good. On your cheat sheet for this lesson, there's an HTML link that takes you to the MathWorks Greek letters and special characters chart. And at the bottom of that, you can see all of the tech options that you can for Greek letters, special symbols, and different commands that are really helpful. All right, next, let's deal with linking our numerical data to our text annotations. So let's start by putting in a text annotation, just like we did last time. Let's put a marker that tells us what our x coordinate and x2 and y2 coordinates are, and then a label that says x2 is equal to 2 and y2 is equal to -3. So when we run that, we'll get those coordinates right next to that second point, and that's really helpful. However, we've got one problem here, is that our data here are defined, and these are actually dynamic data because they're variables. We can change these variables. For example, if we changed y2 from -3 to -2, then what it's going to do is the plot is going to update. It's going to move that point to the y2 is equal to -2 portion. But then our label is now incorrect. x2 is equal to 2, that's correct. y2, it still says is equal to -3. So what we want to do is we want to make this string array, as we see here, dynamic. And the way that we do that is instead of typing in or hard coding the -3, we use just an invaluable command that's called num to string, or num to str. And then what we have to do though is we need to recognize here, well, you know, if I type that in, it's going to just create a string if I run this. So let's try that. And it now writes num to string, so number to string. So I need to separate that from the rest of the array. Now remember, in our arrays, any array, we can put square brackets around our array. And then by putting square brackets around there, we can start to parse that array apart. And so we can close our quotes now, and if we close our quote after that first part, and then we type in num to string, and so it's going to convert that number, y2, to a string, then the array that we have, all connected together, should give us what we were hoping for, which is x2 is equal to 2, y2 is equal to -2. And so now it's now become a dynamic array, and if we run this, it's going to run the code within the text, and then we see that we have our dynamic array back. We have our number, which is correct. It's going to change with the value. Looks like I left off a parenthesis, so I'm going to add that parenthesis back in. Because it's a string on the parenthesis, I need to add an open quote and close quote around it, and then put this inside of the total array. And so now, no matter where we change y2, we can change this back to our -3 and run it. It's now updated the position of the coordinate, but it's also updated the annotation for the coordinate itself. So you're going to find that this num to string command is extremely useful. I use it all the time to create dynamic character strings, and you can use it anywhere that you have an input or an output that's a string. And examples of functions that we've used so far that can have a string input and you can use this type of variable are the DISP, legend we've used before, X label, Y label, and text. And so anything you use a string for, you can always make that a variable string using this command. Now let's finish up by adding this 3D plot to the right side of our 2D plot that we've already generated. And so our goal here is to put this into a single figure, and to put the plot to the right, we're going to use what's called the subplot function. And so if you take a look at your cheat sheet, then you'll see that to use a subplot function, subplot meaning that we're going to put multiple plots within a single figure, then we have a subplot, and M and N is going to lay out the size of the grid that we're going to be using. And so in our plot, we only want 2. It's a side by side, so the size of the grid that we're using is going to be 1 row and 2 columns. And then the last entry into the subplot tells us which one of these to use. So for example, if you look at the bottom of your cheat sheet, this would be a 3x2 grid, and then this would be the first plot up on the top left, the second plot would be on the top right, the fourth one is the middle row on the right, and so forth. And the first thing that we want to do in our code is to create a space for our subplot and our first plot to go onto the left-hand side. So below figure 1, where we've initiated the figure, we're going to type in subplot, and then it's the 1 row, 2 columns, and we want to put the plotting command and actually plot this into the left window. So when we run this, we should get space on the right-hand side and our plot that we had on the left-hand side. So now in the space on the right, we have an opportunity to do what we want. We can put another plot there, you can put a picture there, you can put text. There's all kinds of options, but this is really freeing up that side of the grid, or that panel rather. And so before we add our plotting command on the right-hand side for our 3D plot, we're going to say subplot, and this is still in the same figure that's been initialized, subplot 1, 2, and then we want to look at the second panel. And so if we run this, we now see that we've initiated a grid that has no information in it, and so now we need to put our plot in there. So this is where we're going to put our 3D plot. Now for 3D plotting, it's not terribly complicated. I recommend in this case, let's just copy and paste our normal plot function below here for the 3D plot. Now the function for a three-dimensional plot, 3D spatial plot like we have here, is going to be plot3. So which means that instead of looking for 2 arrays, an X array and a Y array, it's going to look for a third array, which will be our Z array that's defining our Z coordinates. So let's insert that now. And then when we run it, we get a three-dimensional plot. Now, you can see here with this three-dimensional plot, we can rotate this around. It adjusts the scaling as you go. But just like with our two-dimensional plot, there's a couple things we need to add because it's a spatial plot. Let's add our grid on, and then axis equal. And so with these two commands, we should see a better outcome for the actual size of our three-dimensional triangle. Okay, so we have one other problem here. Once we're in 3D, it is really difficult to tell which axis is which one is the X, which is the Y, which is the Z. Now in 2 dimensions, it's really easy because we control that really well. And so the way to solve that is to simply put in labels into your code on your axes. And so to do that, I'll use a similar command that we had in our 2D plot, X label for X coordinates, Y label for Y coordinates, and Z label for Z coordinates. And as we run this, we can now easily see that here's our x-axis, here's our y-axis, and there's our z-axis. Now one thing to note is that the origin is not in this corner. So our 0 is here, our 0 is here, and then our 0 is here. So the origin is somewhere in the middle. So, and you have enough tools right now that if you want to define that origin, put some lines on there for each of these axes, you're welcome to do that. And also note just the ability to rotate this to look at your three-dimensional plots in lots of different directions, and how even when you rotate it, it's going to change these labels to help you orient yourself to the three-dimensional figure. All right, so now we have this beautiful figure, and so what are we going to do with it? What I don't recommend is taking this screenshot, and then after we get this screenshot, going to your Word document and dropping it in there, and just saying, all right, figure 1, and so forth like that. And the reason why is because this just doesn't look that professional. Depending on the resolution of your screenshot isn't that great. The gray background is a little distracting. There's not a lot that you can do, particularly in like PowerPoint presentations. And I said earlier, screenshots are wonderful for a quick email. They're wonderful for posting on a forum or a message board or some text message. Screenshots are wonderful. But when you're writing reports and writing real reports, for Microsoft Word in particular, I highly recommend that what you do is you can get this looking how you want, and then go to Edit, Copy Figure, May take a little bit because it's getting some data out of that. And then just Command V, Control V, and paste it in here. And so now you can see that we have a nice looking white background in your figure that you can use easily in any of your documents, PowerPoint presentations, or anything else where you need professional quality. So hopefully this was helpful in helping you go to the next level in creating your figures. I know that you will have this as an expectation for your future courses, and I hope that you use this well.